Hello, everyone. Today, I will introduce the content related to power consumption. The content of the introduction mainly consists of 4 parts: low power mode, platform power test, current measure, and optimizing current consumption. First, let's introduce the low power mode. Devices can enter low power mode when not in use. In this state, the device consumes less power, but can quickly wake up and resume full functionality when needed. Most components, such as the clock, CPU, peripherals, and RAM, can be powered off to reduce system power consumption. For example, DLPS is a kind of low power mode. The documentation for low power mode provides a detailed introduction to the low power mode. Here, I'll just give a brief overview of the contents included in the document. Our system has a total of 4 power domains: DPD domain, AON domain, PON domain, and core domain. DPD domain is the most fundamental power domain of the system, and it is active when the system is turned on. It contains the necessary modules to bring the system out of low power mode. AON domain provides the power for AON finite state machine to control the clocks and power trails. PON domain supplies power to SRAM, some hardware modules for retention, and the Bluetooth MAC when it is in DLPS mode. Core domain supplies power for CPU and peripheral digital circuits. Peripherals may reside in different power domains on different models of ICs. For detailed information, please refer to the System Power Domain Introduction section of the documentation. Our IC has a total of 2 power units: the system platform and the Bluetooth MAC. First, let's introduce the Bluetooth MAC low power mode. There are 2 modes, active mode and deep sleep mode, with the deep sleep mode consuming less power. For detailed information, please refer to the Bluetooth MAC low power mode section in the documentation. There are a total of 4 modes in the platform: low power mode, active mode, DLPS mode, power down mode, and ship mode, ranked from highest to lowest power consumption. For detailed information, please refer to the platform low power mode section in the documentation. Most of the time, the system is in an idle state and only necessary data needs to be retained for system recovery. Components such as the clock, CPU, peripherals, and RAM can be powered off to reduce system power consumption. When there are any events to be handled, the system will exit from low power mode. The clock, CPU, Bluetooth, peripherals, and RAM will be repowered on and recovered to the previous state before entering DLPS, and then respond to the wake-up event. First, let's introduce the process of entering low power mode. After entering the idle task, interrupts are disabled, and it is checked whether the Bluetooth MAC allows entering deep sleep mode. If allowed, the Bluetooth MAC store and enter processes are carried out to enter deep sleep mode. Then, it is checked whether the platform allows entering low power mode. If allowed, the platform's store and enter processes are carried out to enter low power mode. For detailed information, please refer to the Enter Low Power Mode section in the documentation. When a wake-up event occurs, the system will enter the reset handler to check whether it is the first boot or a wake-up from DLPS. If it is a wake-up from DLPS, the DLPS recovery process will be executed to restore the buffer, stack, I/O, and other elements. Then, interrupts are enabled, and the system jumps to the idle task. For detailed information, please refer to the Exit Low Power Mode section in the documentation. Next, we will introduce how to use the low power mode in practical applications. First, we explain how to configure the low power mode. Users can configure different power modes using these 2 APIs. For detailed information, please refer to the Configure Power Mode section in the documentation. When users want to perform certain actions when entering or exiting DLPS, we provide a way to register a callback to achieve this. For more detailed information, please refer to the Register Callback to Power Stage section in the documentation. Next, we will introduce I/O-related applications in low power mode. Firstly, PAD, GPIO, MFB, adapter, RTC, and CapTouch can be configured to wake up in low power mode. When users utilize the pins, they need to configure them according to the actual circuit to avoid the risk of leakage. Additionally, if DMA is used, it needs to be reinitialized upon exiting DLPS. For more detailed information, please refer to the I/O usage in low power mode section in the documentation. When low power mode cannot be entered, the user can use these two APIs to obtain the reason for the current platform or Bluetooth MAC, respectively. For example, if a timer is added in the code to print the reason for not entering low power mode, and then a log related to the following image is found in the log. The error code 0x5 corresponds to platform power mode error callback check, which means that a registered check callback is blocking low power mode, and the function address is 0x21211765. Next, by locating the corresponding function, you can understand why low power mode cannot be entered. For detailed reference, see the Entering Issue section of the documentation. When an abnormal wake-up occurs in DLPS, the user can enable DLPS utils print wake-up info within app DLPS exit callback to obtain the wake-up reason. When an abnormal wake-up occurs in power down mode, the user can add power down check wake-up reason at the beginning of app main to obtain the wake-up reason. For details, refer to the Unexpected Wake-up section in the documentation. Our IC supports platform power test to help users understand some basic power consumption of IC or assist in analyzing power consumption issues when users encounter them. The document of platform power test provides detailed information about platform power test, and here we just briefly introduce the content included in the document. We mainly support three testing scenarios: static power, Bluetooth low energy power, and Bluetooth power. Each scenario has support for various test items, and users can choose the corresponding scenario test based on their own needs. Before conducting platform power test, we need to do some preparation work. The following sections in the document detail how to perform platform power test. The Settings for Configurations section introduces the configurations required for the MCU config tool. The Settings for EVB section explains the jumper settings on the EVB for testing. The CMD section provides commands corresponding to each test scenario. For detailed steps, please refer to the document. When conducting application power test, we also need to do some preparation work. The current measure document provides detailed information on the tasks required for testing application. The main content includes the following. The EVB hardware environment section provides information on the hardware environment preparation. The configuration section explains the configurations needed in the MCU config tool and DSP config tool. The application section details the configuration required for the application. For specific steps, please refer to the document. Current consumption, or more generally, energy usage, is a major concern for battery-powered products. Optimizing current consumption extends battery life and, consequently, improves product performance. There are three main factors that affect the power consumption of Bluetooth audio SoC devices, including the SoC's static power consumption, the amount of power transmitted, and the total amount of time that the Bluetooth is active. The document on optimizing current consumption provides detailed information on optimizing power consumption, and this is just a brief overview of what the document covers. We will divide the optimization of power consumption into several main categories. First is static power consumption, which is mainly influenced by power modes, DVFS modes, and frequencies. Users need to set appropriate modes based on their application scenarios. For detailed information, please refer to the static power state section of the documentation. The power of RF is mainly affected by the receive power and transmit power. For detailed information, please refer to the RF receive power and RF transmit power section of the documentation. The factors affecting Bluetooth low energy power consumption primarily include advertising, scan, and connection. For more detailed information, please refer to the Bluetooth Low Energy State section in the documentation. The factors affecting Bluetooth power consumption primarily include page scan, inquiry scan, sniff mode, page, and inquiry. For more detailed information, please refer to the Bluetooth State section in the documentation. The above is all the information related to power consumption. Thank you.